You have to meet him.
Okay. Right. So I'm just going to present the slides that I have for us today. Um, all right. So machine learning is all about getting computers to learn patterns. You know, it's about getting computers to learn patterns in your data and then being able to do some kind of predictive, most likely predictive analysis, or just give you insights on what your data is doing right now, and you know what are the next steps. So just about giving insights, trying to find patterns in your data, and then that's just all machine learning is all about. So machine learning and data science workflow. So in a typical data science workflow, um, we have these steps, right? We have the steps. The first thing you do is to collect your data, and this is can be simple CSV files like already collected data. This could be interviews or wherever your data is coming from. It could be from a software, whatever, right? It could be something as simple as just doing an interview and then writing down, typing down your data, probably on Excel or something. And it could scale as much as having data engineers load you data using ETL processes, right? So the point is to get as much relevant data to the goal as possible, right? Then when you get those data, typically in a real world scenario, data is not coming in a clean version, right? So when what we do is we try and find a way to create consistency in data. So there might be, because most likely human beings are imputing the data, or maybe the ETL process. As long as anything that has to do with human beings, as long as human beings are in the procedure, there tends to be mistakes, right? So we might have a data set in which like not all the names are spelled properly, or maybe there are some issues, there are some negative values and stuff, those type of things. So we try and clean the data to make sure that it is consistent. We remove incomplete data and everything. Then we do exploratory data analysis, what we short what we usually call EDA. So EDA is to discover patterns and anomalies with your data. That's what EDA is for. It's just discover patterns and anomalies with your data. So you do things like data visualizations, trying to see what's different of your data. Is there correlation? Is there this? Just trying to make sure like the data is as um you can understand as much as your data of your data as possible. So that's just the point of exploratory data analysis. And this is very key and important so that you will know and have an idea of the limitations of maybe the opportunities you can exploit in your data, or just trying to find out, okay, what is this data saying right now, right? Because if you have high correlation between your features, for example, I'll get back to that in a bit. Then, you know, if you have high correlation with your features, you know that maybe your model is going to test and stuff like that. So preparation is all about preparing the data to transform the data in a way the model can use it, right? So prepare it. You can't. The models we're going to be working with are mostly statistical models, and statistical models don't take in letters, for example. So for that context, you have to, if you're working with statistical models, you have to find a way to represent your data um, in numbers, right? So that's where pre-processing comes in. They also deal with scaling, because if you have skewed, for example, if you have a skewed data set, skewed meaning like maybe most of your data set are between this range, and maybe they are now outliers, right? If you give that to your model will tend to predict more of the ones that have more attributes on it, and your model will perform very poorly. So you should try and scale data and other things. Just make sure that that is whether we are doing encoding word encoding, label encoding, trying to turn text to numbers. Basically, that's what I mean by coding. And then other things, probably scaling and other little things, removing null values, making sure your data is prepared for maybe you represent null values, right? And then making sure your data is prepared for the model. Then you train the model or algorithm on the processed data that comes out from your data preprocessing, and then you do evaluation of your model's performance. So under machine learning, we have different types of learning. And machine learning, just think about it as trying to train up your computer to be able to basically learn something and be able to act based on what it's learned. So we have supervised learning. And supervised learning is very simple. Just think about it as you are trying to learn something, you want the AI to learn something, and you already have to find to train the model to know how to predict the price of houses. Setting is that I'm going to get a data set. I'll have information of houses. So that was going to be like the number of bedrooms, where the location of the house is, things that I feel like will affect the price of the house, basically anything and everything. Then I'm also going to get the price of that particular house. So the model is going to learn, look at the features and look at the price of the house, and then try to learn some patterns between that. So what features best affect the price of the house, right? And trying to understand the balance in what we call weight. So before I move on to all this, machine learning is really built on statistics and probability. Statistics, probability, and calculus, right? So a good understanding of these things will make you excel as a machine learning engineer, because each of these models we are going to talk about, or we're going to ever use in machine learning, are built on the premises of calculus, statistics, and probability, right? So basically, I don't want to sound too technical. I don't want to go too technical in the bits, but we basically have um what we call weights, right? So for each features that we have, maybe we have, by features I mean properties of the house. Features is like the things that you need to predict whatever you want to predict. So your prediction is based on a label Y, and then features is everything that you need to predict that Y. So the weights are significance to those features. So what the model basically does in a very abstracted high level explanation is that it basically gives each of those features weights. So it looks at the price, and over a good number of examples, it now says, oh, this tends to this more, and basically ranks them. And each of those things is what we call weights. So what your model, when we say your model, you're training your model, what you're training your model to do is basically to give weights to each of the features. So maybe location, things like location, number of bedrooms, plot size, and all those things will affect the house more, right? Yeah, but also maybe things like number of windows and stuff might not affect the price of the house as much as that. So that way your model is basically trying to rank um the weight is giving to each of those features. So I don't know if uh, it's clear to everyone. So I'll be using terminologies like features, weights, and all that biases to explain most of these things. But supervised learning is that you have your features and then you have the stuff you want to predict. That's what supervised learning is all about. So the model will provide labeled outputs, the algorithm lists patterns, and then the labeled data pairs. You have the labels to guide the AI learning. For example, very common methods are spam and not spam, which is a classification problem. Classification problem is you have two or more defined classes in which you are going to train your model on. For example, spam and not or not spam, those are two classes. All right. So you are classifying it within spam, whether a mail is spam or whether a mail is not spam, right? Also, we have things like probably classification of faces, like facial recognition, is basically hindsight classification problems. And then we have regression problems. Regression problems are like continuous amount of data, right? So regression problem, for example, is predicting of houses. So house price can range from probably, let us say 1 million to, let's say, 1 billion. And each number between 1 million and 1 billion can be a price of a house. So that's what we mean by continuous, as opposed to having three, four, five features, maybe classifying animals, classifying diseases, classifying cancer, all those type of things, right? That's classification problem. And then we have regression problems. So regression problems, we have regression models for that. Classification problems, we have classification models for that. So basically, those are the two things you would need to understand fundamentally. So when you have a problem, the first thing you are typically going to look into is, am I having a classification problem or am I having a regression problem? And have support vector machines, which I will explain in more details as we go on. So we have unsupervised learning. Unsupervised learning is all about, we want the model to figure out the answer itself, right? The answers. I want you to look into my data and just give me something, some kind of insight. And then we have, under that, we have things like clustering. So I'll give you a very good example. So let's say we are a company and we have a lot of customers, and let me give an example of a company. Uh, yeah, let's say we are a company, we have different products that we sell to different classes of customers of different tastes. Let us say we have three classes of products that we have. Then we want to segment our customers based on their behaviors to probably into lower class, middle class, and high class. And basically, or just something along those lines. Or basically just it might be scaling, classifying them into those groups, right? And then or just basically looking at the customer behaviors, which customers tend to behave the same way, right? So if we know the customers trying to behave the same way, or maybe they have the same spending habits, the same login periods, and other things that might be important to our model, so the model can be able to create clusters, meaning create grouping our customers into those each of those sessions. And then we can now do something like a recommendation system. When we have a new customer, we try and fit them into one of these clusters, and then we are now like, oh, okay, then what do people in what products have the people in these clusters? Let's say Netflix, for example. Maybe you are a type of guy that notice that you like romance, you like this, or maybe you are a type of guy that likes action movies and all that. So they have, let's say we have different users with their different tastes. We try, imagine we are trying to cluster those users, and then fitting each user into a cluster, for example. Right? And then we now say, oh, what have you and these people have similar watching behaviors? What have these people watched that you have not watched? Because the probability that you like what these people like is very high. Then I cannot recommend those things to you. So those are the type of situations in which you have unsupervised learning. That's talking about clustering. Association is finding relationships between variables or entities. So basically, I have this entity, I have this entity, I have this entity. I don't know what relationship is, but I want my model to basically find out what these relationships are, right? For me, the model is just going to look at the data, and we have statistical models for that. Just look at the data and find relationships by itself, find correlations by itself, because we're not really giving it what it should be looking out for. Abnormally detection also, we just have maybe a stream of transactional data, for example, or a stream of logs, or this is most likely used in cybersecurity headspace, in which we want to find abnormal things in our probably stream of our network. So if we want to build something like an ML-based IDS, which is an nutrition detection system, we find abnormalities, and then we flag those abnormalities, right? So we are not the model itself will look through our data, find patterns, find the usual patterns. We're not telling it, right? So to look through our data, find the usual patterns. So the moment something is coming in and it does not fit that particular pattern, it flags it as an anomaly. So you can see again, we're not giving it the answers, right? The whole idea, we're not giving it the answers, it's just going to figure it out by itself. Dimensional reduction is something that we also do in classification when we have when we have high dimensions of data. So we have 2D data, probably just having um two features, probably x and x1, x2, and then as we have older features, so maybe we want to predict the house and really have like the plot size and the number of bathrooms. That's like 2 dimension, and then we can scale that. And there are some algorithms that takes longer time to actually get run those algorithms. Something like SVM, it takes longer time to run those algorithms when we have higher dimensions. So PCA or reduction methods help us to reserve and simplify our data so that we can simply just train simple SVMs, because SVMs are really, for example, by SVMs I mean support vector machines. There are algorithms that are really, really, they really deal with high dimensions, and it's increased computational time. So that's just another. So we have something we call transfer learning. Just going to do a quick one on transfer learning. Transfer learning is just mostly in LLMs or NLPs, in which you want to train a new LLM or NLP with the information that the other one has already learned, right? So maybe we don't want to reinvent or spend a long time retraining the model. Maybe we just want to train a new model, let it leverage on what the old model has learned, transfer knowledge, and then we can add new things to a new model, basically. So it's just like an ML technique. It reduces the training time because, training large language models, we have petabytes of data, and then, we don't want to really spend that much on that. If we don't want to really spend that much on that, we can just, how we train the previous model, let's transfer and then add new things, right? So that's just what it is. Another one, we have semi-supervised learning, in which the model sometimes gets the right answers, but not, we're just trying to show them the right answers, and sometimes it actually gets right answers. So we actually have models for that. Then we talk about deep learning. Deep learning is what most people that's most interesting machine learning. So it's a subset of machine learning actually, and it's dealing more with neural networks, which is like really got hype recently for its way it makes things more structured. And neural networks basically tries to simulate what happens in our brain, but not exactly, right? Because the brain is the most complicated thing on earth. In fact, in our known universe that we know of, right? So it has some principles that has to do with neurology, but not exactly, right? So when we have our neural networks, we are creating a network of neurons. Each of these sample points that is pointed out here are neurons, and these neurons learn a bit of information. So let's say we want to do image classification now, and then we want we have 3 layers. We have the input layer where we input our data, then we have hidden layers. The number of hidden layers right now is 3. It can be more, right? You can have a lot more, hidden layers, as many hidden layers as we think is needed. And then we have output layers to give us the result. So each of these layers is going to learn one piece of information. So for example, if we have images, we can have layers that will get a particular pixels from our images and learn something about it. Another one, then we have activation functions that transfer what this guy has learned to the next guy, and then this guy can learn more and learn more and learn more. And then we have an output layer that just gives us the output. All this again is basically maths and statistics. And if you're not someone that likes maths and statistics, I don't think you should consider ML at all. But if you're someone that does and you're excited about it, it's something that you have to look into to fully grasp what you need from ML. And um, so we have neural networks is more for more complex data like images, audio, unstructured information, and all those things. Not really like only numbers. So when you have numbers, you would most likely it's better for you to use. Most times, it's better for you to use classical machine learning models, right? That's with the supervised learning and all that. Then computational power is significant. This where the use of GPUs really come in, and we have frameworks for this. For this class, we're not going to really talk more about deep learning. I just wanted to introduce the entire concepts of deep learning. But if you want to talk about applications, we have facial recognition, large language models, right? Language models or large language models use this technique to some extent. I mean, if let us say NLP, I think LLM uses, the transformer stuff doesn't always follow this. I mean, it has more complicated things, but basically everything that is more complex than just having numbers, we use this guy. So autonomous vehicles too. So we can use deep learning techniques on video data, audio data, and all those things. So also things like if you have sensors and stuff, that's how we train self-driving cars and all those things. So it's a lot more complex, and obviously, the higher the complexity of your use case determine the complexity of the structure of your deep learning model. You are using CNN, RNN, and all those. But for this class, we're not going to really dive much into that. So I'm just these are just models on machine learning. We have regression models and classification models, so that's supervised learning. And some of the models we have linear regression, we have linear regression, and other things. For classification model, we have logistic regression, which has the name regression, but it's actually for classification using sigmoid functions and all that. We have XVMs. SVMs does well by putting boundaries in your data. So basically, for classification and using boundaries, we have KNA, naive base. Naive base is more based on probability, and we have decision trees. We have random forest. We also have random forest regression. Like we have a lot of models on these things. I'm just listing a few. Reinforcement learning, which is something I forgot to talk about. Reinforcement learning is when you train the model to do something, right? You are it's a, some kind of it's some kind of almost unsupervised learning, except that it is semi-supervised, right? In the case in which the model, for example, if I want to train the model on how to play a game, right? So I can punish the model when it makes a mistake and add a bonus to the model when it doesn't make a mistake. So, for example, if we want to train a model to play Subway Surfers now, so when he makes a mistake, the model gets punished. It's like the way you train dogs, basically. That's just the entire idea of having reinforcement learning, and it works very, very well. That's how you train robots. You can train robots how to walk and all those things through reinforcement learning techniques. Ensemble learning is just about having multiple models. So instead of having one of these models, you have multiple models working together. So we have the bagging technique, the boosting technique, and the stacking technique. We have all those models under it. Then we have neural networks, which I've talked about, generative adversary networks, GAN, or more of Gen AI, recursive neural networks, CNN, RNN, perceptrons are like the simplest form of neural networks, and then we have autoencoders. Then obviously on other unsupervised learning, I'm talking about clustering. We have all those stuff on clustering and all those things. So you as a machine learning engineer, you'd basically have to learn about at least have a high level understanding of each of these models, but most likely also what you know and focus on depends on the problem you are having. So that's why we have engineers and we have researchers. So ML researchers, their job is basically to do research, create these models, create ways, and those are where you really see people around people that create deep sea, people who are in deep mind and all those things. So their job is basically to create these models and do research and really do more of the math. And while the engineers are the ones that actually take all these things. So maybe when sorry, yeah. So maybe when you have typically when you have a new problem, you don't have to reinvent the wheel, especially as an engineer. Your own is just to go through the research papers and understand what this guy did, the technique he used, how it's implemented on data. Can I use that for my own use case? Then after you but you have to have and probability and calculus knowledge, at least the basics. Okay, let us say not say basics, the intermediary knowledge. You don't really need to be advanced except you're into academia, research and stuff. So yeah, so that's just the in terms of using um so essential packages for ML. So we have packages on I'm going to talk about Python basically for this class. So the most popular languages for machine learning is Python or R, right? For this class, I'm just talking about Python. So we have packages already made on Python to help at least the ones we said here are for supervised and unsupervised learning, not deep learning, transfer learning, and all that. So we have NumPy. NumPy basically helps you to efficiently do array computations. NumPy computes faster than using normal Python arrays, and they really utilize CPU very well to speed up your because at the end of the day, what your model is doing is calculating maths basically, and we have functions that it is using on repeatedly and iteratively. So NumPy makes sure those things are efficient and your mathematical function and linear algebra operations. Why Pandas is for more of data frames manipulation. When you want to use analysis, you want to work with your data sets. So that's what Pandas is for, basically. And then we have scikit-learn. Scikit-learn is for, it already gives you already made algorithms, popular algorithms like logistic regression, um, and the likes. So logistic regression, linear regression, random forest regressor, decision trees, random forest classifiers, also things for grid search. And the way it works is it makes this super optimized for CPU usage. So that's what makes scikit-learn very powerful. It's not just the amount of functions it already has and the amount of algorithms it already has, in which you just tune your algorithm. Um, or it's it utilizes CPU very well, and that's what makes it popular over the rest. So, as a data scientist or an ML engineer, you are going to be using this tools a lot, depending on your use case. For deep learning, we have other ones like TensorFlow, PyTorch, you know, other ones, and I think Pandas we now have Polaris too. Polaris is currently faster than Pandas. Right. So the community is basically enriched. That's something about Python for data science and AI as a whole. So the community is already enriched with a lot of tools that you can use, but these are the most popular ones. These are the ones we will be using. And partners use NumPy under the hood. So these are the ones we'll basically be using for our demo. Today, I'm just going to talk about a little bit about data preparation. I think I've talked about this already. So we have cleaning, what cleaning entails, EDA, what EDA entails, and pre-processing, what pre-processing entails. Um, so why do we prepare data? Because number one, I told you like your for classical machine learning models, statistical models, we have we work based on numbers, and they have algorithms for them. But like the algorithms are built off of numbers, so everything you have to do has to be actual numbers. And we can also feed non-values, that's not the number values or null values to it. So we have to talk about, and we also have to check for correlation. Correlation is that if we don't want too many correlated um features together, because to make Times are since they are correlated, meaning probably this one is very close to this guy. We want each of those X variables, which I'm talking, which are the features, to be as independent as possible. So find all those things out when we're doing EDA and then when we are doing processing. And then oh yeah, so these are the tips to build successful ML solutions. Um I'm I'm all this is from all this I'm saying is from a data science perspective, right? There's also an ML perspective. But the data science perspective is that you should try out the right approach. So you should understand your data first, and that's how you do analysis first before you even start training. Understand your data, choose the right approach. Sometimes it might just be simple. Sometimes you have a particular task that you have enable you. You have to go and read research papers, and that's why the research papers there are lots. There are millions, if not billions, of research papers by researchers out there. So based on your use case, you can literally just go read about it. Make sure you are choosing the right approach for your data. Sometimes it's just something simple. Sometimes it can be something complex, depending on the complexity of your data. And that is something that is really interesting about the ML community. We need to have that rich, people. A lot of people doing researches, a lot of people releasing research papers, so that you, for your use case, you just come and find a way to implement what works for this person. If you feel like it works for you, you try and experiment with it on your data. So maybe you're not getting the right results, you can go online or go to Google Scholars, check on research papers or research gates, find research papers, read research papers based on what works for you, find the approaches that works for you and use it. Then you have to prioritize data quality. Now, the quality of your data, um, literally, it has a one-to-one relationship with the accuracy you are going to get, right? So if you're doing image classification, for example, there's a time I was doing image classification. My model was, I used CNN. My model was superbly built. The architecture was superbly built. But I understood that the reason why I was getting these low results is because of the resolution of the pictures that I was working with. So what I did was the resolution, and I had a very perfect result. So in that type of scenario, the quality of your data is a one-to-one relationship with the kind of stuff you have. So that's why quality assurance of data is very important, especially if you're working with organizations. Is something that the data engineers will speak well to. So data quality is very important for ML. If you have poor data, your ML will learn nonsense, and you have bad results, right? So relevant data, making sure that the data that you have, you can also do things that like feature engineering, creating new features based on what you already have that will help, you think will help your data. Well, and then we now leverage Python ecosystem. We have specialized libraries for efficiency and reproduction. So you don't really have to really code out the entire algorithm again. Maybe when you are learning about the algorithms, it's probably best for you to try and code out your small algorithm so that you can, because when you try and code it out, you understand really what the algorithm is about and you cannot forget it. But when it comes to production, we don't want to waste time building your algorithms from scratch. So we leverage things or people has already built. So we have scikit-learn, for example. If you have a Spark network for big data analysis, you're probably going to use Spark Emily Heap, you know, also TensorFlow, PyTorch for deep learning models and all that. So you have to leverage Python ecosystem to make your job very successful and not to waste time. And then it's all about running experiments, right? So as an ML engineer, you run basically a lot of experiments and you have to refine your approach each time. So sometimes your model, there's this concept of overfitting and underfitting, in which your model basically learns, and because you're training it on this particular amount of data, the model is not learning to generalize. So as much as you want your model to learn about these patterns, you want your models to be able to work on new data, right? And see data that it has not seen before and have a good performance on it. So we don't that's why we constantly update our models. of overfitting, there are also techniques to mitigate underfitting and overfitting, making sure things like making sure your data is not skewed, scaling up the data, scaling your data between a particular range, so that every distribution of the data is kind of equal. So you don't want skewed data, you don't want all that, and then you have to run as many experiments as you can, right? As many experiments as you can, trying to experiment with your data, trying to see, oh, is this after I train this model, test, or I'm seeing the accuracy. Um, Accuracy does not always define the full story. That is the difference between an ML engineer and a researcher. A researcher would basically focus more on accuracy, most times on accuracy. But in real life scenarios, things like fairness comes in, things like making use trade of accuracy to make your data, your model more generalizable. Or sometimes you can have both of two words. Sometimes due to fairness, for example, let's say in your data set we are trying to classify something. If one let's say fraud, there are a lot more frauds that have been non-fraud transactions, right? I'm talking 90%, sometimes 98% to 2%. Organization only 2% of stuff is fraud. So if you leave your data like that and give it to your model can have a 98% accuracy, and all it is doing is just predicting that it is not fraud all the time. But because 98% of your data is not fraud, the model would show on paper that it has a 98% accuracy when you look into what the model predicted and what is actually what actually is the correct answer. I'm talking about supervised learning. And you might see that it has 98% accuracy. Meanwhile, that's because it might be predicting not a fraud every time. And if your model is predicting not fraud every time and it's getting 98% accuracy, and you're like, oh wow, it's having high accuracy, the model is not doing anything. It's a very, very useless model, right? Also things like false positives, false negatives. False positive is just for example, things that are not fraud that the model classified as fraud. And then we have false negatives, things that are fraud that the model classified as not fraud. So up to you, depending on the business. For example, you might care more on false positives than false negatives. And false negatives and false positives. Meaning you might have to do a trade-off. Though you try and strike a balance, you might have to do a trade-off of amount, because if you have maybe your model is really good at detecting fraud, but also takes some other things that are not fraud are fraud. And normally, if you have false positives, your customers become angry because each of their transactions, their normal transactions, is as fraud, your system is not allowing it through. So things like that, all those biases and stuff are the difference between ML induction and ML in research. Are the differences. The things we care about are different. Our goals are different. ML in real life is a lot more complicated than the way ML is in on paper, on research paper. That's that as an ML engineer, you really have to think about. It's something you have to really, really, really think about. So my trade-offs, I have to make trade-offs. I might not be able to get the best. How do I find a balance? What should my balance be? Those are the things that make ML solutions successful. Another thing I would say that makes ML solutions, the ability to reproduce and version. So we have things like MLOps. MLOps is just basically after the data scientists have done their jobs, basically making sure that we can reproduce the same result. So meaning if I train something this time, I should be able to reproduce the same result the next time I training, which is a problem with ML in production again. Because ML algorithms based on certain biases change. So we have ML ops, something like ZenML, DVC for data versioning, ZenML for ML pipelines. That's basically to make things reproducible, and also experiment tracking, knowing ability to track your experiments and knowing, oh, I'd run this thing before. So instead of creating different notebooks and try starting again, and having many notebooks. We can have a tool like ZenML and MLflow for experiment tracking that track your experiments, plus the artifact and everything, so that when you can go back to the previous result of the experiment without really having multiple files, right? So those things are what makes full ML solutions. And then when it comes to deployment of ML models, that's another thing entirely. How do people use your model? Things like, oh, how do people use my model? The servers my model are running on. Um, how do I change? So if I could change my model, for example, in fraud detection, when you don't want to change the model, maybe you have retrained after, like, when you have more data, you have to continually retrain your to improve your model's feedback. So maybe there's a, even in cybersecurity too, when there's a the way frauds are being done tend to change over time. There are new attacks every day. For example, if you have your ML model that is predicting particular attack, you have to retrain it on new data to add what is new. For example, right? But when you want to make that change in your model, let us say you've already trained a new version of your model, you want to make that trade, you don't want a situation in which when you are taking down your model and you're putting in a new model, that the entire system that checks for your cybersecurity is down. And within that time, anything that enters just enters. We don't want that. So things like, things like that are what separates data scientists and ML engineers in retrospect. Right? Though the terms are used together in some sense, but like that's the difference between the ML engineers or ML engineers and the data scientists. The data scientists, their job is just create the model. But everything after creating the model, inside creating the model, orchestration of those model creation, experiment tracking, and all those things are what ML engineers do typically. So all these together, when you have a good data science back team, or maybe you're the only one, if you have a good solid understanding of both data science aspects, that's in model training and all that, and orchestration on model deployment and all those things that tend to deal with more of ML, you a complete package. Like you are that's what anybody in the market, right? So that's all for the questions. Quick demo of what will things will look like. Very short demo. So are there questions?
Right. Thank you for me. Please, if there's any question, move on to more practical part of it. Right. If you are not comfortable on your mic, you can drop the questions on the chat. Right. Where's questions? Okay, your hand is up. You have it through now.
Just a quick one. So, Shay, when you were speaking, you did mention something about underfitting when the model, like the percentage. So, at what percent would you be able to tell that the model you built is fairly okay? I know most times when you have a model that does 100% prediction, you should be careful of overfitting. And once you have a model that doesn't do the classification very well, then she also be mindful. Is there any rule of thumb to say, haven't built this model and you tried it, or the percentage of the correctness of your model is this? Is there any rule of thumb to say, I think when it's fall within this category, I think it's fairly okay, or it depends on the model you are building?
See is there. Number one, there are ways algorithms that help you with overfitting and underfitting to detect, and there are algorithms already built on the platform. Another thing is train your right. One of the best ways for you to know whether your model is overfitting and underfitting is likely when you show it new, like completely new data. For example, I can train my model if I have models in years. Let us say I have my data set in maybe for 2015 to 2016 or 2016 to 2017. One of the best ways I can know my model is overfitting, just giving it more examples already. Sometimes it's also you would know from the stats, um, from the graphs of training. Do you understand? Especially when you're training deep learning models. So by the time you join the graph of validation, your validation data set and your error percentage. So at some point you expect that your errors are basically going down as you are progressing in iterations of your training. I'm speaking from a deep learning perspective because we have something called epochs. It's like the number of iterations. So by the time you notice, you draw your graph of your training and you're seeing the percentage drop in errors. If your graph starts to go back up, so let's say it's going down, down, and it's going down, or it just drops down, and at a point it starts going back up, you know that okay, there is an issue. For other ones, you probably would find out when you use your test data sets, and more data generalized. So you split your data sets typically into simplest way to split it is training and test. You can split it into training, validation, and test. And basically, by the time you use training and validation and you work on it, you bring in completely new data. If your model has overfitted, you will typically know. For example, you've trained your model, and let us say let's say I want to train my model to um know my face, right? So I have pictures of my face. Side view, this are different lighting. So how I will tell my model is if I bring in a new, completely different picture that is not my face, and then the model starts predicting it as my face. So, or maybe I am in a very different background, and then the model starts predicting this is as my face. You know that okay, your model has really overfitted. But there are also little algorithms to know. But typically, just test when you go to your test, you know that okay, your model is completely overfitting on the train. Maybe you go to your validate, so your validate to probably test the model, then you have your test data. The test data will tell you straight up that this model is overfitting or underfitting. Obviously, underfitting, you will know that the predictions is going to be very hard. Right. But for deep learning, you basically draw a graph of your training per epoch, so your loss per epoch, and then you start seeing the graph going down because it should be descending. But at a particular epoch, it might be ascending. Then you know that okay, there's something wrong. If your graph is not like very smooth and it's just edgy, you know that there's something wrong. Obviously, also sometimes it might be the number of epochs. So maybe you are training it too many times and it starts trying to confuse itself. You understand? So you start seeing in your graph for you to know. So
All right. Thank you. I believe Ina. All right. I don't think there's more question. We can change.
okay. I want to quickly set up the test. I'll be the stuff so that I can share my screen. So just give me 1 minute to quickly do that. Um, okay. Sorry, just give me a moment. Sorry. Okay. So I'm presenting my screen now. Um, okay, so this interface that you are seeing is Google Labs, and it's a online interface, a free online interface for you to basically run your Jupyter notebooks. You can also run your Jupyter notebooks locally using uh, Anaconda or just using your VS Code and downloading an extension, which is what I would advise because Anaconda is a very heavy application. So basically, I'm just going to run through this as fast as I can for time, but um, I might not be able to go through as in the maybe next as a particular time. You can now go through, the syntax, learning that and all that. But for now, it's just this. So we import our values. I think I have set up to just import necessary libraries. Um, this is scikit-learn. We also have setting up Seaborn. Seaborn is for plotting, Matplotlib for plotting. The rest of the things are just like the models I see from scikit-learn. I will also need XGBoost for what we are going to do. Great parameter tuning. So let us say we have what we call parameters. Parameters parameters are like, let's say parameters are things that in a model, let us say we have this algorithm, and then the algorithm we have probably like constants and variables that makes up the algorithm. So parameters, when you set a parameter and put in your data, you expect some particular kind of result every time you run that with the same parameter. So what you try and tend to do is that your model learns different weights, these weights, which is like ranking the importance of your features in some kind of sense based on the parameter you give it, right? So hyperparameter tuning is a way of, oh, let me see the best combination of parameters that gives me the best results. So that's what we did CSV is. So the point of this data, this cache demo is just to predict how much data a particular um, unit will need in the year. So basically looking at the previous um let us say the idea of this is just you have your data, you have, let us say you have units in your company, and you want to, you just want to predict that, oh, you are supposed to divulge money to these units probably every year. So these units need, so that when they come with their to you, or let us say you have different shops, when people come, you know that they are not cheating you, they're not asking for more money, but they actually need to blah blah blah. So that's just the idea of this data. So understanding the data is very important, so that you can always import your data here. And then when you go to Collab, it's very easy. You can literally go to Collab right now, collab.research.google.com, and create your first stock. So this is we kind of each of these talking about the environment, each of these things are cells. So we run things independent of each other, basically section our stuff like this. And we can use markdown and code. So we import the libraries, right? We get our data sets, and then we begin cleaning of the data. The data can be gotten from cargo, which is like Cargo, which is a online place in which you have data sets. So you just download this data set of your choice. We really just did. So you fill in all values, right? I've already pre-run this thing, so that's I'm not running it again. We So, because I understand time has gone. So basically, we do data cleaning, like I said before. We are filling in no values with zero. We can't have no values. We are now doing trying to create new features, really and trying to clean this data. For example, putting this guy in a date time format, you know, making sure that all the formatting is the same because we have different formatting. We have months, we have monthly, we have a month, day, year, we have day, month, year, and depending on your data format. Just basically put everything in. We do a bit of feature engineering and feature extraction. This guy is speaking to feature extraction, trying to extract out of the date time format the days of the week, the months of the week, you know, the days of the week, the months, the day of the week, and other things. Then we can now get rid of the actual original date time formats later on. So we are just trying to extract more things that we feel like is necessary or useful for our data. Then we already clean that date time format, so we don't need to do it again. We don't need them again because we already extracted the information that we can't have date time formats in our model. We can only have numbers. So we have to do away with that date time format and we're able to extract numbers from it. So day of the week is 1 to 7, on Monday to I'll be 0 to 6, sorry, Monday to Sunday. Then we have day of the month 1 to 12. Basically numbers. I mean, the month 1 to 12, the day of the month is 1 to 30 or 1 to 21. Is a weekend is 0 or 1? Is it true or not? The day of the week, and that's how we just get all those things done. So we now get rid of the things we don't need at the end of the day. Then we are using a model called random forest regressor, which is a linear we're doing supervised learning because we're going to be showing the model, the data, and then the actual cache they actually demanded. And then we have random forest regressor, which is like a model for doing supervised learning. Um, these are now the parameters that we use, n estimators and random states. Random states is to make sure that we can reproduce because the model is going to models are built on probably like a normal distribution, and we want to ascertain the seed of that distribution that it uses. So that we can each time we run, we should get the same answers. Then this is the guy that we're actually dealing with. Number of estimators to be 100. Not too much on random forest. Just a random forest thing. Then we fit our data. Basically, this is where we fit the model to the data. That's where we are training, and then we can now make predictions. Make predictions doing this, and then we can now see the mean squared error. Um, as you can see, the error maybe I should go out to score. Should probably have used out to spot so that you can see it in like percentage. But basically, this is the error. So what this is calculating is that it's calculating the error percentage. So it's going to use the formula actual minus the actual minus the sorry, the predicted minus the actual gives the error, right? Divided by the um the mean distribution basically, and then we have this. So we have squared errors. We're going to square the error and then find the mean. The root mean squared error is finding the root of that mean, basically. So then we now have this hyperparameter tuning. If there's an error, create search. Okay, I think there's a problem here. I'll have to fix that. But basically, what we are doing here is very simple. We are trying to these are the number of parameters that we want to have, and these are the values of the parameters you want to test. So hyperparameter tuning is going to be one of the most computationally expensive things you can do in ML because it's going to use what we call the brute force method in stuff. So it's going to test for each combination. So we're going to have a model for when an estimator is 50, 10, 2, when it is 50, 20, 5, when it is 50, 10, 10, and all those. So you're going to like this now. We should have about how many models? If you calculate this is 3, 2, 3. We should about maybe 20 or 30 something models to get each of them having a different combination of each of these. And yeah, we are not comparing. So this is going to take, if we have to run this now, it's going to take a lot of time to run compared to just training one model. But it's for us to see that okay, we let us assume we are very satisfied with our model. We want to see what is the best parameter we can use for the random regression model, as you can see here. So we have to perform what we call a grid search, which is basically train different models and then compare. So at the end of the day, we can be able to compare the models, which okay is not going to show here. We're going to compare the models and get the best parameters, right? And then after we do that, we can see the one with the best parameter was max depth as 20 and estimators as 150, and we also have another reference as 42. And then the rest of this is just like printing out the predictions out. So then we can dump the model in some kind of pickle file for deployment later on. So basically, this is how the workflow runs on. And we would normally have a lot more experiments than this based on our use case. So right now we can see that we're only testing one model, which is random forest regressor. So we're going to test multiple models to try and find which one is the best for our use case. We can test linear regression, we can test or maybe decision tree on regressor and other SVMs. Is there SVM regressor? Yeah, I think so. Yeah, I think SVM regressor too. Okay. I think SVM is classifier. Sorry. So we have SVM regressors and all those things, right? So yeah, we just basically test as many models, we do parameter tuning to them, and other things. You can use XGBoost, you can use assembly method, trying to add multiple models together, and all those things. So those type of things will are the things we typically do before we just deploy, right? Or before we choose the best out of it. I'm going to stop sharing and show you cargo. So let me share again so that I can show you cargo, which is like a place where you can get your data sets. Nice. Sorry. Okay, so I'm just going to show this. So this is cargo. This is where you get your data sets. You can get data sets to learn. You can also learn on cargo too. There's this learn place where you just have quick understanding of basic things, quick understanding on SQL. I used this a long time ago when I was just starting up. Never really completed it. That's what we have this year. Then you can have quick intro of pandas, quick intro of this and feature engineering. Maybe over time, we'll have webinars like this to teach each of these concepts to you in terms of pandas. But like if you want to right now have a quick understanding, not too advanced but very simple understanding, you can go to Kaggle. Also, Kaggle also have discussions panel in which when you have your problems, you can start a discussion and somebody will answer it for you. Then you can see codes of other people. You can also run the way we have Jupyter Notebook, we have collabs. You can also run a notebook straight from Kaggle, right? Maybe you can see other people's codes that they decided to make public so that if you want to learn, you want to sit down on your particular data set, you can just search and then be able to find that. You can see the models. Models are, probably already trained models, most likely your LLM models, which is not for this class. And then we have most importantly data sets. So you can always go for competitions if you are confident enough. They have really good competitions. I think the average we have the free ones, so just challenging, and we have these ones that are more complex. when you build up your skills, you can see this one, the price one is $1 million, this one is $440 million, and all that. So it's just like an entire platform for data science. But what is most interesting to us right now is going to be this data set space in which you can search on your data set. For example, if I should search linear regression, you can find data sets for linear regression, right? So if you have a salary data set, you have student performance data set. So for you to just basically learn, and for example, if I should click this data set, some people would have done this and use these data sets and put the way they implemented their own workbook there. So in which you can basically skim through, maybe you're doing your own, you want to see how other people did theirs. You can also go through, you can always start a discussion and ask your questions, and also make suggestions, basically. And then yeah, basically that's just what this platform is used for. So you get your data set, you download that book here. You can also create your own data set. You start a notebook here. You can or use Google Colab. So if you're using Google Colab, you just import the data set into your or you can start a notebook here. And as you are learning, you can learn and you can start. But I'm hoping that as more time goes to have depending on the interest of the people that are here. So yeah, so with pandas, you can learn a little. You can also use YouTube to learn if you want to buy courses. But Kaggle is always a good tool for you to use, especially when you are prepping yourself for probably interviews and all that. You can find, depending on the way you can search, you can also search online for data sets because at some point you can get simple data sets from Kaggle. There's some Kaggle data sets that are harder than that are simpler than the others. Um, but you can get simple, intermediate, and more advanced data sets. So you can prep yourself. You can prep yourself, go for competitions. Um, basically, if you win the competitions, get money. Things like that. Just build yourself, and then creatively, you can now. If you are now a guy who's depending on whether you want to go or going through the path of being an ML engineer in terms of ML ops and deployment and orchestration, you'll also be able to do that. So I hope there let me just questions. Let's see. So are there any questions?
All right. Thank you, Seyi, for that wonderful section. It's quite impactful. So right now, we can now accept questions. If you have questions regarding, how you might start off to learn this, or any specific question regarding what he said during the session, you can, speak it out now, and or you can drop it on the chat below.
Seems like there are no questions.
All right. So I think in absence of no other question, I appreciate everyone here tends to go home with one thing or the other, right? And let's forget, please, you can follow us on our social media: Facebook, YouTube, TikTok, LinkedIn, all the social medias. We have our presence there, and we then just at Data. Make sure follow, like our video. This video now, this section is already live on YouTube, and as well after this live, you will also see the recorded video there. Make sure that you like, follow, and we'll keep you posted. All right. Once again, thank you everyone for hopping on this call, and see you next 2 weeks for a wonderful session